hear me? Is it still glitching, Siddhika? Okay, so it is now. Oh, it's not glitching. Okay, good. Good. So now let us start and yeah, in the last class, what have we done? So you were not there, I guess. Rishita was were not here, and in the last class, we finished this topic force due to right Kepler's law and force between two masses, right? The Newton force between two masses. These things were in the last class. Oh, internet is so these are things and so many questions written in the last class, right? Now let us move on and in today's class I will talk about acceleration. Acceleration due to gravity at different right? That I will talk about. And so we have three regions, right? Know that what is the force, right? Let's say we have an object. This is uh, this is the surface of the earth. This is the surface, right? And some object is at this place, or some object is at this place, or some object is at this. So let me make a spherical, right? So let me make a spherical surface and then so let's say this is our Earth, right? And this is the radius of the Earth. And some objects are at here. Let's say at the depth. Some objects are at the surface, and some objects are at a height h from this surface. Let's say this is the height h. And yeah, these are some objects whose mass is m, and right. And then let's say the mass of the Earth is m or capital. So force of gravity at these different positions would be different, right? So force at surface would be out. That would be simply G M M by R E square, right? And let's write it as R E as R. This would be this at surface, and at some certain height. At certain height, this would be GMM divided by R plus H. So this would be at a certain height. And then we have, and then at a certain depth, so at certain depth, this would be GM. But now the whole mass of the Earth is not contributing. So that would be M prime, and then this is R minus D. So these are the forces that are uh, that are applying on these masses, right, at a different position. So due to different forces, right, we can calculate the gravity at different places. So this is, let's say this is at surface. So this would be simply F surface by M. So this is simply GM by r square, right? And similarly, we calculate the gravity at certain height. And when we solve this, so this comes out to be 1 minus h by r. And similarly, when we solve this at depth, so this comes out to be 1 minus d by r. So always the maximum acceleration is at the surface, and at different places you have different acceleration due to gravity. Right? Is it clear to you? Is it clear? And you already know that how do we get these results, right? How do we get these results? So derivation is not that important. You already know the derivation, right? You remember the derivation. Yes, remember the derivation. Let me write all the things. M is mass of the earth. Small m is mass of the object. And then RE, and that I'm calling it as R. This is the radius of the earth. And then D is depth, and H is yes, I got this. Yeah, these are the things that we have to put in, right? So this is G, this is G at certain height, this is G at certain depth, right? Okay, the screen is still yeah, I'm connected. Fine. Okay, so this screen is still loading. Let's stop this. Then if I share it, okay, so it is taking some time. Yeah, why this is still. Yeah, can you hear me? Can you hear me, Siddhika? Hello, Siddhika, can you hear me? Oh, now it is. Okay, can you hear me, Siddhika? Hello, Siddhika, can you hear me? Yeah. Okay, so yeah, some internet glitches are happening, right? Okay, so these are the gravitational acceleration. Yeah. Okay, yeah. Sorry about that. Right. Okay, so this is about the gravitational acceleration at different places. Now, the potential energy, right? Potential energy due to gravity. So that is how much? That is, let's say if this is the mass, right? And this is the source mass. Let's say that this is the source mass. Let's say this is Earth, right? And this is the source mass M. And then we are calculating the potential energy at this point, and this is the test mass, right? Potential energy of this thing due to this R. And let's say the separation between them is R. So potential energy is simply defined as minus G M M divided by R, right? So if you are at certain height, let's say this is your Earth, right? And this radius is R. And if you are at certain height, right? And this is the mass, and this is the mass of the Earth. This is H. So then your potential energy due to this mass M would be how much? That would be simply that would be simply minus G M and M R plus H, because that is the distance between the center of the Earth and then this mass. So this is the gravitational potential, and this is very useful. So whenever we take an object from, let's say, some this point to this point, so your change in potential energy, change in potential energy, that gives you work done. That is delta U, and that gives you work done. So if you want to calculate the work done, so work done would be simply W, which would be U final minus U. So remember, this is a very important relation. And then there is another very important quantity, which is gravitational potential. So this is denoted by V, and this is simply minus Gm divided by R, right? So we just divide the potential energy by the test mass, so then we'll get the gravitational potential, right? So gravitational potential is minus Gm by R, and gravitational potential energy, that is minus Gm by R. So please note down these things, and then we'll, on the basis of these things, we'll the questions. Please note it down. Right, I guess the internet has problems. Let me check that. Right. Now it is. Yeah, and whenever you want me to scroll down the screen, please tell. I'm using different devices connect to the internet. Now Wi-Fi. Yeah, whenever you want me to scroll it down, please tell. So as because the forces between the masses are changing, that is why you get different acceleration, right? Because force is mass into acceleration. So if you change the force, then your acceleration will change, right? And simply you can calculate the acceleration by dividing the test mass. You divide the test mass, these small m's are the test mass, so then you get whenever you want me to scroll down the screen. Yeah, whenever you want me to scroll down, please. Yeah. Okay, then please note it down and then we'll do the questions. Yeah, whenever you have a step, please. Good. So now to understand these concepts, let us do some questions, right? Now let us do some questions. Okay, so what is the depth at which the value of acceleration gravity becomes 1 by n times the value that is the value that the surface of the Earth. Right? We know that what is right. So what is the depth at which the value of acceleration to gravity becomes 1 by n times the value that the surface of the Earth. So we know that what is the gravitational acceleration at certain depth. So that is G1 minus d by r, right? And we have to calculate this right. In this question, we have to calculate this d. And in this question, they have given that this GD becomes 1 by n times the value of G. Right. So this is the thing that they have given. So we can put the value of G in here. So G is 1 minus d by r, and that is 1 by n G. So we can cancel this G, right? Then what is the value of what is the value that we will get? So this is n minus, or let me write it as 1 minus d by r. That is 1, right? This n goes over here. So I can write n minus n d by r, that is 1. Because I want to calculate this d, right? So I have to somehow simplify this thing so that I get d in the left hand side. So I take this thing in the other side. So this will become minus nd by r. And this is 1 minus n. This minus is here. I can take it the other side. So this will become r and minus 1 by n. Is it clear? Satika, is it clear? Yes. Is it clear, Satika? Yeah, is this clear? Yeah. So then please note it down. So, yeah, good, good. Because this is the information that they have given. This thing we already This thing we already know. They have given this information. Gravitational acceleration becomes 1 by n times the surface. Right. Please note it down, and whenever you have noted, please tell. Yeah, whenever you have noted, please tell. So done. Good. Okay, so now let us try the next question. Right. Let us do the next question. So a body weighs 72 Newton on the surface of the Earth. What is the gravitational force on it at a height equal to half of the radius of the Earth, right? So they are asking that, right, force is, so they have given at the surface of the Earth. So the object is at here, right? And the force is how much? Force is 72 Newton. So because weight is what? Weight is the force due to gravity. That is weight, right? Force is so mg and that is the weight. So this is 72 Newton, right? And then they are asking that what is the gravitational force on it at a height equal to half of the radius of the. So what would be that? So we know that this would be how much? So they are asking that the now object is at a height. So this is r, and now the object is at a height equal to half of the radius of the. So from here to here, the height is r by 2. So this is the height, right? So now we know that what is the force acting on this object? What would be the force? So force would be Gm, mass of the Earth, divided by R plus H whole square. So that is the force at this height, right? Because the separation is R plus H, mass is M, and by Newton's law, this would be the force, right? But they have given the value of, so they have given the value of this H. So this H is R by 2, right? So then we can write this as GMM, and this is R plus R by 2, which is 3R by 2. 3R by 2 whole square. So this would be how much? This is GMM, and this is 9R square, and this 2 goes upstairs. So this is 4, right? And now we have to figure out this value, GMM by R square. So this is 4 by 9 GMM by R square, right? So this value we have to figure it out. This thing we know that is 4 by 9. So if we come at this part, this information, so this is at the surface, which means that the force acting between this thing and this thing is how much? So this is GMM divided by R square. Yeah, so I got disconnected again. Now it is. Yes, so is it clear to us, Deepika? Please note it down if it is clear. Please note it down. Okay, so today I'm facing some internet issues. Right. You please note it down and yeah, please note it down. Yeah, whenever you have noted it down, please. Okay, good. So now let us do the other question as well, right? Yeah, so the same question, but in a different right. So let us do this question. So a body weighs 200 Newton on the surface of the Earth. How much will it weigh halfway down to the center of the Earth? Right. So this is the question, right? And yeah, so this at the surface of the Earth again. This is this is 200 Newton, right? And let us directly write that this is what? This is Gm and mass of the Earth divided by r square. So this is the value which is given. Now we want to calculate how much will it be halfway down to the center of the Earth. So remember, we can only use this thing, right? 1 minus d by r. So this is only applicable when your depth is very, very smaller than this r, right? Otherwise, we have to only use the force. So we can only use the force, right? If this is applicable, then we use this thing. Otherwise, we have to use the analogy of force. So force at depth, this would be how much? So this would be, let's say this is the mass and this is the total mass of the Earth, right? and then at a certain depth we are taking. So this object is at certain depth, right? So this is r, and this distance is how much? This distance is depth, right? So the radius, this is the total radius, and then the object is at certain distance at certain depth. Now, if we calculate the force between this center and this mass, then we have to assume this mass of the earth, because only this mass of the earth is contributing, right? And this is m prime. This is m prime. So how can we relate this m prime with this m, right? So let's say that this distance is r, right? And how can we relate this mass with this whole mass of the earth? Because we know that f at depth, this would be m and m prime. Now the whole mass of the earth is not there. This mass is contributing, right? And the distance between this thing and this thing, because whole distance is r and this distance is d, so this would be r minus d, which we have written r, right? Let me, if, as of now, let me write it as r. So this would be the force at a certain depth, right? Now, how do we write this mass prime? So, what is the constant for this Earth? What do we assume that that is constant for Earth? What do we assume? So we assume that density is same, right? So whether we calculate the density at this region, whether we calculate the density as a whole, so density is same. So mass by volume, that would be same as mass prime by volume prime, right? So because this is a sphere, so what would be the volume? Volume would be 4 by 3 pi and capital R cube. And this would be how much? This would be m prime 4 by 3 pi and r cube. So 4 by 3, 4 by 3, pi will cancel, and we will get mass prime as m r cube divided by this r cube, right? So this is the new mass that we get. So then we calculate the depth. Then we calculate this depth. So this is m, and this is m r cube divided by r square and this r cube. So this r square and this thing is cancelled. And what do we get? So we get g m and m by r cube. And then this r is r minus d. Right? This is the r that we have taken. So then if we take out this r term, so what would be that? This is g m and m. And if we take out this r, this is r cube, and this is 1 minus d by r. Oh, so we'll get the same result. So this would be g m m r square 1 minus d by r. Right, so this would be how much? So we know that this value we have already gotten. This value was how much? This was 200 newtons, right? Oh, so we can use this result directly, right? So there is no, yeah, so this is applicable for every depth, right? So every depth this is applicable, because we have just proved now that we didn't assume anything, right? To derive this thing, we didn't assume. So yeah, this is applicable every. Okay, so this value is 200 Newton. Depth, they have said that this is r by 2 and this is r. So this r will cancel, and how much we will get? This is 1 minus 1 by 2. So this is half. So 200 into half. So that is 100. So this would be 100 newtons. So this would be the force at this depth. So force is maximum at this surface, right? The force was 200, the weight was 200 at surface, but it will reduce to 100 Newton, right? It will reduce to 100 Newton at that depth. So is it clear? Is it clear to you? Yeah. So we can also directly use this thing because we know that F depth would be how much? That would be mass and G depth. So this thing we can directly use. So this is m, g depth is g, 1 minus d by r. This would be direct. And we know that this much value is 200. This is 200 that they have already told us, right? So this value is 200, 1 minus r by 2 by r. So this would be again 200, 1 minus 1 by 2. So this is again. So we can use this thing, right? Using the acceleration, or we can solve this whole thing. So both the ways we can solve. Right. Please note it down, and if you have any doubt, please ask. Is it clear to you? Is it clear, Siddhika? Yeah. So then please note it down. Right. Please note it. Okay, the internet has returned. Let me check that first. Okay, fine. Actually. Yeah, I got disconnected. So is my screen visible to you, Siddhika? Is it now? It is. Yeah. So please note it down, and whenever you want me to scroll it, yeah, whenever you want me to scroll it down, please tell. Then, okay, so this part also noted. Okay, yeah. So please, right. We can use both the methods, right? This one is quicker. So yeah, we should use this one, the right hand side, right? This one is quicker, so we should use this one. But right, if we yeah, if we don't know this relation, then we can use yeah. Whenever you have noted it down, please tell. That okay. So now let us try a different kind of question, right? And let me see if we have gravitational potential energy, gravitational yeah acceleration. Is the surface of the Earth. So let us do. Then we'll do the questions on potential energy, right? So these are the questions for acceleration, and then we will do some question on uh, potential energy. So the acceleration due to gravity at a height 1 kilometer above the Earth is same as at a depth deep below the surface of the Earth. Right. So for the height case, right? For the height case, this is 1 kilometer only. H is 1 kilometer, and radius of the Earth is 6,400 kilometer. Right. So this H is pretty small than radius. So we can use this thing. The height is G 1 minus 2h by r. So this result we can use. And yeah, depth one. So depth one we can, for any case as we have just seen, that we can use GD as 1 minus d by r. So this is applicable for every depth, right? But this is only applicable for this thing. This we have to do. Now the height is only 1 kilometer, so we can use both these things. So they are saying that the acceleration due to gravity at a height 1 kilometer above the Earth is same. So they are saying that, right, acceleration above the Earth and at depth, both the acceleration are equal, which means that so the acceleration at the height, this is equal to acceleration at the depth. And then we can write this value. So this is G 1 minus 2h by r. and this is g 1 minus d by r. So this thing gets cancelled, and the value of height they have already told about that. So we can also write 1 minus 2h by r and 1 minus d by r. So this will also cancel, right? Because if we take 1 in the other side, so 1 minus 1 would be 0, so 1 is also cancelled. Then we have this minus minus will cancel, right? So h by r, that would be d by r. So r will cancel, and d would be simply 2h. And we know the value of h, right, already. So that is 1 kilometer. So this would be, depth would be simply 2 kilometers, right? So if you have an object which is 1 kilometer above here, so it will experience the same force as 2 kilometers below. So at both these positions, the force would be the same, and acceleration would also be the same. So acceleration at height would be equal to acceleration at depth. This is what we get. Is it clear? Depth would be 2 kilometers. Good. So then, please, down. Yeah, please note it down. And then we will do the questions on potential energy. Yeah, whenever you have noted, please tell. Then, okay, so now let us do some questions on potential energy, right? And we already know that what is the potential energy, right? So let us do some questions. And this is also the gravitational potential. Okay, so this is the question. Assuming that the gravitational potential of an object at infinity is zero, right? So this is the initial condition. The change in potential energy of an object of mass m when taken to a height h from the surface of the earth, right? So we have to calculate the change in potential energy. And what do we already know? We know that the, let's say, these are the two objects. Right? Let's say this is the mass of the earth, which is the source mass, and this is earth. From here, we are getting the gravitational potential. And let's say the separation is r. This has some mass m. This has some mass m, which is the test. So as we have already discussed, that this would be minus g m m divided by r. Right. This minus is important because this tells us that this is bounded. Right. So yeah. So this is the potential energy. Now, initially the object is where? So initially this is the earth, right? And the object is at the surface. This mass is at the surface and this has the, so this separation is r. So we know that this is the initial part. So initially this would be how much? This would be minus gm m divided by r. So this is the initial gravitational potential. Now this has been taken to a height h above the surface. So final final position is what? This is your this is the earth, right? And then this object is taken h above the earth. So this total would be the separation, right? So then you final would be how much? That would be minus gm, and this would be r plus h. So this is the final potential. Now, what would be the change in potential? So change in potential is how much? That is u final minus u initial, and that would be how much? This would be minus gm m by r plus h, and minus of minus gm m by r. So this would be how much? So this minus is there, and this would be gm by R. So let us take GMM common, right? So we can take GMM common. So this is, let me write the positive one first. So this is this minus the negative, right? And if we solve, right, so if we solve this thing, this is R plus H. So R divided, this is R plus H minus R plus H divided, this is simply R. So this part will cancel and this would be how much? This is GMM H divided by R plus H. So this would be the change in potential. GMM H by R plus H. GMM H by R. This would be the. Okay, is it clear to you? Yes, is it clear? Tika, is it clear? Yeah, then please note it down and yeah, please. Yeah. So whenever you want me to scroll down the screen, please tell. Yeah, give me one moment. Yeah, whenever you have noted it down, please tell. Yeah, whenever you have noted, please tell. Okay, so now let us do the next question, which is also based on this potential. What are you saying? Oh, okay, yeah, okay, obviously.